Good morning. So, in the last three lectures, we have been looking into the measurement of displacement, and in today's lecture, we'll be looking into measurement of pressure and strain. And before we go into this, let's first refresh. What do you mean by pressure? What do you mean by strain and stress? Okay, so the definition is well known that pressure is the force applied per unit area. So if P is the force that is being applied, then the sigma is the pressure that is forced by area. Okay, and the strain is when this force is applied, whichever object on which this force is applied, whether it's a tensile force or compressive force, it would experience a change in dimension. So the relative change in dimension of an object upon application of the force is called as the strain, which is given by this epsilon. Okay, while pressure is a quantity with dimension, say for example it is Newton per meter square, or it can be written as pounds per square inch. The strain is a dimensionless quantity. Okay, and stress that is applied on a object is the force per unit length of the per unit dimension of the object. Okay, so those are the definitions. Proceeding further, so in this lecture we'd be looking at measurement of pressure and also strain. Okay, so when we're talking about pressure measurement, there can be direct measurement or indirect measurement. So by direct measurement, what we mean is that the applied force is directly translated to a displacement which is measured using a dial, okay, or some other direct measurement of the so the displacement is calibrated. So we measure the displacement directly and the force is calibrated based on the displacement. A few examples of this is for measurement of force. You have transducers like the Bourdon tube, Bellows, or diaphragm, and for measurement of pressure, and for measurement of force you have spring or a proving ring. So these are, so in this case, whatever these transducers are acting as primary transducers. Okay, on the other hand, you can also have cases where there is an intermediate step of transaction. So in this case, what is happening is that the pressure that is being measured, okay, is causing a dimension change in the transducer, and this dimension change is again translated to a electrical quantity. Okay, so for example, what we have is a strain gauge. So in a strain gauge, you have a wire, okay, whose, so by application of pressure, the dimension of this wire changes, okay, and this change in dimension causes a change in the resistance of the wire, and this resistance change is measured by an electrical circuitry. Okay, so what is happening is that now whatever is the object to which this which is called, whose dimension is changing. Okay, so in this case what is happening is that, let us say, I'll give an example of this. So you have a proving ring here. We could have used the proving ring directly and measure the displacement of the proving ring, or we could put a strain gauge on that. Okay, so the displacement of the proving ring is translated to change in length of the strain gauge. or change in dimensions of the strain gauge, which in effect causes a change in resistance of the strain gauge, which is again picked up and measured by an electrical circuitry. So in this case, you have a secondary transducer. So you have a primary transducer here and you have a strain gauge as a secondary transducer. So you have an indirect measurement also. And in a case, you have a strain measurement here. Okay, so similarly, the pressure can cause a strain, and this strain in effect causes a dimension change, and this dimension change in a piezoelectric crystal is going to produce a voltage by this piezoelectric effect. Okay, so in addition to these direct measurement, you have this indirect measurement where there is a secondary transducer involved. Okay, we'll look at both of these types of transducers. Okay, so first let us look at the primary case, the direct measurement case. So you have a probing ring. So in a probing ring, you apply a force, and this force causes a dimension change of the probing ring, and that is directly picked up. So here you have a picture of a probing ring. So in the direct case, what is happening is you apply a force here, and when this apply a force, depending upon it being a tensile or a compressive force, okay, the dimensions of this probing ring are going to change. Okay, initially it is a circle. So when there is a compressive force applied, then it squishes in one direction and it sort of elongates in the other direction. Okay, and when there is a tensile force, it goes the other way around. It gets elongated in the longitudinal direction and gets squished in the lateral direction. Okay, now this change in this dimension can directly be picked up, okay, by a gauge, and this change in dimension can be translated to the force being applied. Okay, or as I mentioned earlier, you can also use a secondary transducer like a strain gauge, which can be bonded onto this probing ring, and this dimension change of the probing ring is translated to a change in resistance of the strain gauge, and this change in resistance is picked up by another electrical circuit. Okay, so that is as far as the probing ring concept goes. Next, we do have springs which also can be used as a force measurement transducers. You would recall the usage of control or springs as control elements in the electrical meters, in ammeters, in analog ammeters and analog voltmeters. And what you might have observed is that the force that is exerted by the spring is proportional to the displacement. Okay, so what is happening is that the change in the length of the spring, okay, from its resting position, okay, will be proportional to the force being applied. And this can be done in various types. And you can have a cantilever spring in which the deviation from this position is proportional to the force that is being applied. Okay, the same can be talked about in case of a helical spring also. Okay, and you can also have torque being measured, okay, in a torsional bar, okay, where the torsion here is being captured by the so it captures the torsion, captures the torque that is being applied. Okay, so in this manner you can use the concept of springs for measuring force, the rectilinear forces F or torques tau, okay, and in both cases you would have either you have a torsion of theta or a displacement of x being indicative of what is the force being applied or what is the torque being applied. Next, we have the concept of a Bourdon tube. So the Bourdon tube is basically a tube which has a one end that is open and the other end is closed. Okay, and the pressure that is to be measured is applied from the open end, like here. Okay, or in this case from here. Okay, or in this case from here. Okay, in this case from here. And the other feature is that the tube itself has a non-circular cross section. Okay, and basically the operation principle is there is a pressure difference. So if you apply a higher pressure or a lower pressure than the atmospheric pressure, there is a pressure difference between the inside and outside of the tube, and that causes the tube to that causes the Bourdon tube to try and equalize the pressure across its cross section by trying to attain a more circular cross section. Okay, so from this, so if a pressure is increased inside, if a higher pressure is being applied, what is happening is that the Bourdon tube tries to attain a more circular shape. And by trying to attain this more circular shape, this tube will start to unravel. So if a higher pressure is being applied, this tube starts to go for a higher radius, try to go into a circle of higher radius, into a shape of a circle of higher radius, that in turn has moved this tip from one position to another position. So this variation in the position can be captured by a set of linkages, mechanical linkages, and that can be translated to an indicator, to a pointer, and the pressure can be read. Okay, so based on the application, you can have a Bourdon tube that is of a C shape, you can have a spiral shaped Bourdon tube. Okay, and this also has a torsional effect. Okay, you can have a helical Bourdon tube. Okay, so based on the particular effect, you can have different types of Bourdon tube that can be used depending upon the application. Okay, so here is a schematic of a Bourdon tube and also a picture of an actual Bourdon tube in action. So this red arrow indicates the inlet. So when the pressure is increased, you see that this end cap is moving, and that due to the linkage is being translated by some mechanical linkage to a motion of a gear that is placed here. Okay, we are not able to see the gear because it is behind this bar, and this gear is actually translating all those, the movement of the gear is captured in a on a pointer that is placed on the circular disc. So it is on the other side, you're not able to see, but you can easily imagine that this motion is going to cause this pointer to move in this manner. Okay, and if there is a graduated scale here, it is obvious that we are able to read pressure. Okay, now coming next, okay, we have bellows and diaphragms. They are also devices that directly change pressure to displacement. Okay, just like the Bourdon tube. Okay, now in a diaphragm, it's basically a membrane or some plate made of some flexible material that is secured say on a surface secure to a to a base along its circumference, and the center is free to displace. Okay, and it is displaced. The center is being deflected because of the pressure being applied. Okay, and due to the flexibility of the material of this diaphragm. Okay, and the concept of a diaphragm is really simple, because we have a diaphragm that is in our ear, that is responsible for the hearing. So any change, any air pressure change is being detected, is being translated to small deflection in the diaphragm, that is being picked up by the mechanism or the nerve mechanism in your inner ear, and that is being translated to electrical signals, and you're able to basically hear. And similarly, you have a diaphragm in your chest, and the displacement of the diaphragm is what is causing your lungs to function. Okay, in any case, what is happening is, whenever there is a pressure difference, the diaphragm moves from this position to, say, to a different position, and this deflection delta D is proportional or is dependent upon the pressure that is applied here. Okay, we can even, so you can have diaphragms that are of different configuration. You can have a single layer diaphragm, a flat diaphragm, or you can have a diaphragm where there is a corrugated layer in between, and this sort of gives you a better resolution than a flat diaphragm, however not much. And you can even have a case where two diaphragms are sort of joined together to make a capsule. Again, this has higher sensitivity than the flat diaphragm, however the scope is much less. Okay, the deviations that a diaphragm, or the deflection that can be expected from diaphragm, is quite small. For larger deflection, for larger sensitivity, what you would need is a bellow. So a bellow is basically functions like a pressure activated spring. So you have thin walled tubes like this. Okay, and when a pressure is applied, these tubes again will unravel to a shape, and basically the end of this bellow, the displacement of this end of this bellow, is going to give me an indication of what is the pressure being applied here. And you can also use the bellows, in addition to measuring absolute pressure, they can also be used to measure differential pressure by connecting two bellows in which two different pressures are being supplied to, and they are connected by a rigid wire here, and the deviation of the wire from its mean position, okay, is going to give me an indication of this difference in pressure P1 minus P2. On the face of it, it appears that because of higher sensitivity, the bellows are going to be a better choice always. However, again, everything comes at a cost, because the frequency response of a diaphragm is better. Okay, so depending upon the application where you have, whether sensitivity is more important or frequency response is more important, you would need to choose whether you want to go for a diaphragm or a bellow, or altogether a different transducer. Okay, so here you have a picture of a bellow based pressure gauge. Okay, so as you say that, as we can see that when the pressure is applied, the bellows expands, and that sort of gives us the indication, and the control spring sort of gives the counteracting torque, so that the pointer goes to appropriate reading. A pointer goes and stops at the appropriate reading. Next, we come to the main part of this lecture, which is the strain measurement. So in case of a strain gauge, what we are basically doing is to use the fact that when you have a metal conductor, okay, when you have a wire that is stretched or compressed, then the resistance of the wire changes. Okay, so when it is stretched, what is happening is that its length changes, its cross-sectional dimension changes, so delta D is happening, and the resistivity can also change. Okay, and the resistivity change is called as a piezoresistive effect. So you know that R is equal to rho L by A. So the cross-sectional area is changing, the resistivity may change, the length is definitely changing. L and A are definitely changing, rho may change depending upon the material. So the strain gauge, which is also called as a piezoresistive gauge, uses this effect of change in resistance to measure strain. Okay, typically strain gauges are only used as secondary transducer. That is, they are not used to measure displacement directly. Okay, the reason for that, so they are used in secondary transducer where you are basically measuring pressure or force, okay, or acceleration or temperature. Okay, and that is, so these primary quantities are changed to some strain, okay, some strain and some displacement delta D, that is translated to a strain, that is translated to a change in resistance, and that is being measured. Okay, so it is never direct measurement of delta D. The reason for that is that generally these displacement that is produced and the strain that is happening, okay, is really in micro range. That is, for the change in resistance to the actual resistance is approximately of the order of 10 raised to minus 6. Okay, so which would mean that we are only measuring, we will only be seeing a displacement or deviations, okay, of the order of 10 raised to minus 6, which are really not useful to be measured as resistances. So in effect, what I want to say is that the strain gauges are not used as primary transducers, they are used as secondary transducers only. Okay, so the strain gauges can be of different types. You can have an unbonded or a bonded strain gauge. In a bonded strain gauge, the entire strain gauge setup, so you have this wire whose resistance is to be computed, or change in resistance is to be computed, is bonded to a substrate, and this entire substrate is bonded to the object whose strain is to be measured. Okay, that will be in the case of a bonded strain gauge. In an unbonded strain gauge, you simply have the strain gauge wire being wound on this setup. Okay, and so when a force is applied, you have two sets of wires here. So you have wires 1 and 2 being here, and 3 and 4 being here, strain gauge wire windings 3 and 4 being here. Okay, now what is happening is that when this is when the force is applied, 1 and 2 are in compression, okay, and 3 and 4 are in tension. Okay, so now when you use a Wheatstone's bridge to measure EO, and assuming that when at balance all the windings are of equal length, or sorry, equal resistance, that is at zero pressure or zero force, okay, R1 is R2 equal to R3 is R4. If you assume this, then when a force is applied, what you have is, because of the compression, R1 and R2 change in one direction and R3 and R4 change in a different direction. Either if R1 decreases, R1, R2 decreases, R3 and R4 increase. So which would mean that there would be a what do you call, a voltage difference that is produced across these two terminals, and that output voltage can be indicative of the change in resistance, and that in turn will give us how much strain is there, which can be correlated to how much force or pressure is being applied. Okay, so in this way the strain gauge can be used as a secondary transducer. Okay, we'll go into the specifics of how this Wheatstone's bridge can be used later in the lecture. Okay, so to be able to make use of how the resistance changes and to relate it to the strain, we should actually go into the mathematical relationship between the strain and the change in resistance. Okay, so let's say, so if you have a strip or a wire made of an elastic material, and you subject it to tension, okay, that is, you stretch that material, what is happening is that the length is increasing and the cross-sectional area is decreasing. Okay, now if you assume, or what you assume, if we know that the resistance of a piece of wire is going to be rho L by A, where rho is the resistivity, L is the length of the wire, and A is the cross-sectional area. Okay, now if a tensile stress S is applied to it, this is going to cause some length change and some cross-sectional area change and probably some resistivity change. Okay, so the change of R with respect to S, dou R by dou S, can be simply be expanded to be equivalent to the change of length to S, change of area to S, and change of resistivity to S, and they can be related in this manner. Okay, now if we try to find what is 1 by R dou R by dou S, okay, and use the formula of R is rho L by A, you can simplify the relationship to be this. Okay, again you have this relationship, and now in addition to this, if we assume we know that the strain is going to be less, the stress is going to be small. Okay, so this change sorry, because we want to really know what is 1 by A, we don't have A as one of the parameters. Okay, I missed one point. We don't have area as one of the parameters of interest. We want the cross-sectional dimension. Okay, so if you have a circular cross-section, we are interested in how D changes, or how the change in D is affecting the resistance, not the change in area. Okay, so we want to translate dou I by dou S into dou D by dou S, or 1 by A dou I by dou S into dou D by dou S. Okay, so what is dou I by dou S? If we assume a cross-sectional area that is circular, it's related to the diameter in this relationship. So 1 by A dou I by dou S can be written as 2 by D dou D by dou S. Note that this sort of a relationship, okay, this sort of a relationship is not confined to only circular cross-section. It is valid for any cross-sectional shape where the area is proportional to square of cross section dimension or lateral dimension. Okay, so if you say the lateral dimension, the radius of the wire, okay, or the diameter of the wire is d, then a is, if since a is proportional to d square, you would have 1 by a dou I by dou s is 2 by d dou d by dou s. Okay, now going further, what we have said is that 1 by r dou r by dou s is going to be this particular equation. Okay, now we have this concept of a Poisson ratio, which is the ratio of the transverse strain to the axial strain, okay, or the lateral strain to the longitudinal strain. So it basically is minus dou d by d by dou l by l. This minus value, okay, is because we know that when the length increases, the radius is going to decrease. So when dou L is going to be positive, dou D is going to be negative. So since nu is going to be required to be a positive quantity, what we want is to be positive quantity. So what we have is this as minus dou D by D. So in any case, this substitution is going to change our equation to this relationship. Okay, now if we assume that all our variations are small, okay, so dou x by dou s can be replaced by del x by del s. Okay, so replacing that and just removing all the del s that were in the denominator, what you end up with is this relationship that relates del r by r with del l by l. Okay, and you have del l by l here also, which is an indirect way to show the lateral strain. Okay, now you have this concept of a gauge factor, which is the ratio of per unit change in resistance to per unit change in length. So it is basically relating del r by r with del l by l, where del l by l is the strain epsilon. Okay, so gauge factor is actually del r by r by epsilon, which if you substitute is going to be 1 plus 2 mu divided by del rho by epsilon. However, in most material, the resistivity is not going to change much with change in length, because at least not at the scales at which the strain is being subjected to in usual application. So you can assume that del rho is going to be equal to 0. So which simplifies the gauge factor relationship to be 1 plus 2 mu, where mu is the Poisson ratio of strain gauge material. Okay, now let us look into the few circuits that can be used for getting the electrical output out of the strain gauge. The simplest way is to connect the strain gauge in a circuit and measure the change in the output voltage. Okay, this sort of circuit is called as a ballast circuit. So you have a strain gauge here, okay, and you have another resistance called as a ballast resistance that is connected in series, so that when the strain gauge resistance changes, there is a change in output with respect to the input. Okay, so the output is going to be Rg by Rg plus Rb times Ei. Okay, and so in the unstrained case, this is going to be the value, and when there is a strain, okay, the relative change in E0 d E0 by dRg, okay, is going to be Rb by Rb plus Rg square times Ei. Okay, from that we can just say that dE0 is this expression. Okay, the change in the output is given approximately by the expression on the right hand side. Okay, you can, this expression can be modified a bit, okay, by multiplying and dividing by Rg, so that I can get the strain relationship out, because drg by dr drg by rg is just like delta rg by rg. This is going to be gf times epsilon. Okay, so you have this relationship now, this expression, to say what should be E0, what should be the change in, what would be the change in the output. Okay, now the maximum sensitivity occurs when both the ballast resistance and the strain gauge's unstrained resistance are equal, and that would be this expression 1 by 4 ei by gf into epsilon. However, it should be remembered that epsilon is going to be the range of, say, 50 to 100 into 10 raised to minus 6. So it is in micro strain. Okay, and gauge factor is typically, say, less than 10. It's basically 2, 4 or 5, something like that. It is not a very large number. Okay, so what you end up with is that the change in the output is going to be 1 by 4th into gf into epsilon times ei. Okay, so the change in the output is going to be of the order of 10 raised to minus 6 times ei. Okay, a few times 10 raised to minus 6 ei. Okay, so maybe let us say it is 10 raised to minus 4 times ei. On top of that, you see what is the unstrained output. The unstrained output is rg by rb plus rg. Okay, when they are equal, this is going to be half times ei. Okay, and if you see the circuit, what you are measuring is the actual output. So after the strain is being applied, what you are measuring is E0 plus dE0 is the measurement. Okay, so let us say that let us say you have a 10 volt input. Okay, so in the unstrained case, E0 was 5 volts. Okay, and when you strain it, delta E0, the change in the output is, and let us say you have a strain of, say, 50 into 10 raised to minus 50 microstrain is being applied. Okay, and then let us say your gauge factor was 4. I am taking typical case. Okay, so what you end up with is that your epsilon or your dE0 is going to be just 50 times 10 raised to minus 4 times your input ei. Okay, 50 into 10 raised to minus 4 times 10 volts. Okay, this should have been 50 into 10 raised to minus 6. So if it is 50 into 10 raised to minus 6, okay, and you have this and ei is 10, what you end up with is 5 into 10 raised to minus 4 volts is the delta E. Okay, so what you want to measure, you want to have you are expecting that you have an instrument that can differentiate between 5 volt and 5.0005 volts, which is not practical. Okay, you can't have a meter whose resolution is 1 in 10 raised to 4. Okay, you can't have 1 in 10,000 resolution. Okay, that's not possible, and hence this Bellows circuit seems to be useless if you are going to measure static strain. However, they can be used to measure dynamic strain by using this capacitor. You can easily measure or easily detect change in strain. Okay, and so dynamic strain can be used, the Bellows circuit can be used to measure dynamic strain. However, for static strain, you have to use some other circuits. Okay, and as we have seen earlier while talking about the proving ring, the circuit of choice is going to be the Wheatstone's bridge. Okay, so when you are using the Wheatstone's bridge, you can again adopt two different strategies. Okay, you can either balance the circuit after the strain gauge is strained. Okay, or you can directly measure, you can use the detector and as a galvanometer, and you can measure the deflection and base and compute the strain from this deflection, from the amount of deflection. Okay, so you either have a null type bridge or you have a deflection type bridge. Okay, let's look at both of them. Let's first look at the null type bridge. Okay, so first we assume that the unstrained bridge is balanced and straining causes a change in resistance to be delta Rg1. Okay, now if the balance is restored by changing R2 to R2 plus delta R2, we can easily calculate that delta R2 is related to delta Rg1 by this relationship, and from which we can say that but our delta Rg1 is related to the strain epsilon by this relationship, from which you can backtrack and find the expression of the strain to be delta R2 by GF times R2. Okay, and this is under the assumption that Rg, all the resistances in the unstrained case are going to be of equal magnitude. Okay, and if not, you just add the factor of R3 by R4 to this. Okay, but that rarely matters. What is of concern here is that the problem that we have in the Bellows circuit, we had in the case of the Bellows circuit, still exists, because we know that epsilon is of the range of 10 raised to minus 6 to 10 raised to minus 4. Okay, so what you are basically expecting is that you are able to move R2 by a factor of 10 raised to minus 4 and expect it is possible. That is, if you have a 100 ohm resistance, you are saying that you can change the 100 ohm resistance by changing the position of the wiper in a potentiometer. You can change the resistance from 100 ohm to say 100.01 ohm. Okay, and that seems to be not a practical or not a feasible thing to do. So again, the null type instrument is not going to be of real use. Okay, what you can do is try the deflection type instrument. So here what you do is that you don't reset R2, R1 changes or Rg1 changes, and you simply measure the deflection D. Okay, so the change in potential between these two terminals is going to be R4 by R4 plus R2 minus R3 by R3 plus R1. Okay, R3 plus R1 is now R1 has changed from to Rg1 plus delta Rg1. Okay, times EI. So this again would mean that if you assume that all the resistance are equal, this output simply changes to this thing times EI. Okay, and which again, if you substitute, okay, you get this expression delta Rg1 by Rg1, which is actually the strain, not the strain, which is Gf times strain, okay, by 4 plus twice this quantity. However, we repeatedly have encountered that this ratio is going to be far less than 1. Okay, there is going to be a microstrain and hence a microscopic change in the resistance only. So the output can be approximated by ignoring this term. It can be approximated by delta Rg by Rg by 4, which translates to gauge factor into epsilon by 4 times the input Ei. Okay. So the other problem that we have is that the resistance of a strain gauge is basically a resistor. It's a metallic wire. So when there is a temperature change, due to the temperature change, there can be a change in resistance also. So if only one of these arms of a Wheatstone's bridge is going to be a strain gauge, okay, then the variation in the resistance due to the temperature change may not be properly captured. Okay, so to counteract this, so we can use strain gauges or at least resistance of the same material in other branches also to offset and to offer a temperature compensation. So this can be done in multiple levels. That is either by using a dummy strain gauge in one of those arms. That is, you have a strain gauge that is not really not subject to strain. It only acts as one of the arms of the Wheatstone's bridge. Or you can have two active strain gauges. So two strain gauges are subject to strain appropriately, or all the 4 arms of the Wheatstone's bridge can be active gauges. Okay. Again, we will look at each of these scenarios and see what are the advantages that are happening here. Okay. So let us look at the case with the dummy strain gauge. Okay. So here you have 4 arms of the Wheatstone's bridge. 2 arms R2 and R4 are usual resistances. They are not strain gauges. And Rg1 and Rg3, 2 adjacent arms, are strain gauges, where you have Rg1 is the active gauge and Rg3 is going to be a dummy gauge. They are made of the same material with the same temperature coefficient of resistance. Okay. However, only Rg1 is subject to the load, it's subject to strain. So Rg1 changes due to the temperature. Rg1 also changes due to the strain. Rg3 changes to the due to temperature. There is a variation in Rg3, but it is not strained at all. Okay, so when there is no strain and the temperature is also at the expected nominal value, you have this relationship Rg1 by Rg3 is R2 by R4. Okay. Now, when there is a change in temperature, okay, there will be a change in resistance both in Rg1 and Rg3. Rg1 will go to R1 into some change, okay, some factor of k delta t. Okay. Now, even after this ratio is going to remain the same. Okay, so the bridge remains balanced. However, what should be remembered in this scenario is that, so this bridge will again behave like the water bridge circuit, okay, that we have seen earlier, the Wheatstone's bridge with the quarter bridge, where only one of the arms is a strain gauge. Okay, so the case where you have temperature compensation with only the dummy gauge, will also behave like a Crotter bridge. Okay, and what should be noted, however, is that this either the other two resistances R2 and R4 should either be made of material that are not temperature sensitive to resistive temperature sensitive. The resistance should not be so temperature sensitive, or of same material. Okay, so R2 and R4 be made of the same material, so you would again have K1 delta T in the other side of the equation also. So this is also balanced in that sense. Okay, instead of R3 being a dummy gauge and sort of not being useful in improving the sensitivity of the instrument, we can make R3 or RG3 here also being another active gauge. Okay, however, to be of any use, you should RG3 should actually enhance the strain. Okay, enhance the sensitivity of the instrument, and that is why RG3 is placed in a way such that when RG1 is in tension, okay, RG3 would be in compression. Okay, now this circuit where you have two active gauges is called as a half bridge circuit, and the way it is improved sensitivity is by this method. So when there is a load, RG1 increases, RG3 decreases by the same factor. Okay, because the tension here is translated to a similar compression on the other side. Therefore, the change in the voltage, the output voltage, is given by this expression, which is GFEI by 2 epsilon. So this is twice sensitivity of quarter bridge. Okay, so so by using RG3 now, you have first of all provided some temperature compensation, and on top of that, you also improve the sensitivity by making this as an active gauge. Okay, now when you can use when you can make two of the arms of the Wheatstone's bridge as active gauges, why not make all four of them as active gauges? Okay, so now in this case you have all the four arms being active gauges with RG1 and RG4, okay, being together in tension or compression, and RG3 and RG2 again being together. Okay, now when you have these four axes, or not four axes, the four active gauges, then you have this expression, and now when you use it, okay, you will get again a doubling of the sensitivity. So this delta E0 is now minus GF EI by epsilon. So this is 4 times sensitive. Okay, however, it should be noted that the price of a strain gauge is going to be much more higher than the price of a resistor of equivalent value. So the price or economy to sensitivity, okay, this trade-off should play a part in deciding which of these three circuits, whether it's a quarter bridge or a half bridge or a full bridge, what should be used. So the price and the sensitivity would determine which of the circuits is to be used. Okay, now we come to the load cell. Okay, now in the load cell, this also is or employs a full bridge circuit. Okay, and again you have two gauges R1 and R4 being mounted. Now here what is happening is that you are measuring, two of the gauges are measuring the longitudinal strain, okay, of this member, okay, and of an elastic member, and two of the gauges are measuring lateral strain. So what you have here is that when two of them are under tensile stress, other two will be under compressive stress. Okay, what is happening is that when there is no strain, if we assume that all the four resistors are equal, when there is strain, because R1 and R4 are mounted along the lateral side, okay, their what you call their resistance will increase by a factor of epsilon, okay, the strain. Okay, however, R2 and R3 are mounted on the transverse side. Okay, so when you have something like this, two of them are mounted like this, two of them are mounted on the other side like this. Okay, so they are going to measure the lateral strain, which is mu times E, okay, rather minus mu E, where mu is the Poisson ratio of that elastic member. So mu is the Poisson ratio of this material or this member. It is not the Poisson ratio of the strain gauge here. Okay, it can't be determined from the guard factor of the strain gauge. Okay, mu is the Poisson ratio of the elastic member, and of course the output is given by this expression, which when you simplify would turn out to be this one. Okay, however, we really know that delta R by R is going to be a very small quantity, so this gets approximated to 1 plus mu by 2 divided by delta R by R EI. Okay, or 1 plus mu by 2 into epsilon into EI, or not epsilon here, it is EF epsilon into EI. Okay, so this sort of we can written as 1 plus mu by 2, but we are not really interested in determining epsilon. We are just trying to relate. So we can also do that into GF into epsilon into EI. Okay, so this strain now can be taken from this. Okay, the amount of strain can now be calculated and related to the output. Okay, here we have a picture of how this happens. So when there is a force that is applied, two of the arms are in tension and two of the arms are in compression. Okay, and that gives us a reading. Okay, so these are the references that can be referred to for the pressure and strain measurement topics. Okay, that we come to the end of the lecture. Thank you for your patience.